This is Joan who will talk about decoders for the surface code.
Right. Okay. Thank you, Frank. Yeah, thanks very much for the invitation. Last time I was at the Newton Institute, I was a mathematical physicist, and now I come back as a quantum engineer. So it's quite exciting to be back, actually. So yeah, today I'll be telling you about the local clustering decoder, which is a real-time, adaptive hardware decoder for the surface code. My goal today is to unpack this title, basically. There's a paper that you can read in the archive, and it's about to appear in Nature Communications. So before I start, I also come from a company, so let me tell you a little bit about what we do. So at Riverlane, we're focusing on a very specific part of the quantum computing stack, and that's the quantum error correction stack. And that means we do things like transpilation from logical gates to physical gates, but then also communicating with the control system in order to implement quantum error correction protocols, and then managing all the data that has to do with quantum error correction. And quantum error correction is a very complex, massive, real-time data processing problem. And to illustrate that, I've drawn here the QEC cycle, the quantum error correction cycle, which is the bit of an error-corrected quantum computer. And then at the bottom of this cycle, we have the physical qubits that we are manipulating. We are continuously collecting error data from these qubits that we need to process in a decoder. The decoder has a job of going from some indirect error signature to a best guess for the error that has happened. And once we have the outcome of our decoder, we need to talk to the control system to do any adaptations we need to do based on the errors we have decoded. This cycle needs to close at extremely fast speeds. In the fastest qubit types, we expect to be receiving error syndromes from the physical qubit once every microsecond. And that's the rate at which we need to process this data. And not only we need to be extremely fast, we also need to deal with gigantic volumes of data. So we have estimated that the amount of data processing that error correction needs for a large-scale application of an error-corrected quantum computer is on the order of hundreds of terabits per second. And to put this in context, this is the same as the bandwidth that Netflix streams globally. And then at the beating heart of this QEC cycle is the decoder. Sorry, I have gone. It's the decoder there at the top. And a good decoder needs to satisfy three requirements. So first of all, as I have said already, it needs to be high throughput. So the decoder needs to be able to process the data at the same pace it's being given to it. Otherwise, what happens is that you accumulate your homework and you basically stall the quantum computer, right? So the decoder needs to be high throughput. It needs also to be low latency, which means you want the decoder to be fast. So it needs to be able to cope with the data in real time, but it also needs to do it quickly. And that's because you want your quantum computer to be fast. So if your decoder is slow, you're going to be slow at doing your logical operations, and we want our quantum computers to be as fast as possible. And finally, and not less importantly, the decoder needs to be accurate. And that's because a decoder that's accurate gives you better guesses for the error that has happened in your QPU. And that means that it's boosting the performance of your quantum error correction protocol, which means that you can do more with fewer qubits. So an accurate decoder will lower the price tag of your quantum computer because with fewer qubits, you will be able to do the same job. So today I'm going to tell you about the local clustering decoder, which is a decoder that satisfies these three requirements. It's high throughput, it's fast, it can be tightly integrated with a control system because it's implemented on an FPGA. I will explain what an FPGA is later. And it's accurate, and the main feature that makes the decoder accurate is that it's adaptive. And adaptivity is a name I'm going to be repeating over and over during this talk. And it's the main feature that enables the accuracy of our decoder. And for us, adaptivity means that we can, at runtime, update our error model that we're using to decode our qubits based on data we're collecting about these qubits. And this adaptivity feature unlocks lots of accuracy features you could implement with your decoder. I've listed some of them here. The one I'm going to be focusing on is leakage. So I'm going to be talking about a specific type of error that's called leakage and how you can decode it accurately using this feature called adaptivity. These are pictures of my collaborators. This was a very special collaboration within Riverlane. It's really a mixture of engineers and scientists that made this work possible, and it was really a pleasure to do this work. And the plan for the rest of my talk is to remind you about the surface code and decoding the surface code. And I'm very thankful that Alex has laid the basics already. Then I'll tell you about leakage, which is this noise source we're targeting specifically in this work, and how to decode more accurately by being leakage aware. And then I'll tell you about the hardware implementation of our decoder, which, as I said, it's distributed. Well, I haven't said that, but as you will see, it's distributed, flexible, and adaptive. And then I'll show you some data of the performance of our decoder, which lives in a piece of hardware in the lab, and you can do experiments with. Right, so I'm now going to remind you some aspects of the surface code, which is the code for which we're going to be doing decoding today. So the surface code is a very old code. Well, very old. It's almost 30 years old. It was discovered by Kitaev in the late 90s. And it's old, but it's good. And it's good because it has a number of great properties, including that it has a very high threshold, which means it can deal with relatively noisy qubits. We know very well how to do error-corrected logic with the surface code. Then, importantly, the surface code can be implemented in architectures that have two-dimensional connectivity. So that means, for example, if you're printing your qubits in a wafer, you only need to make your qubits interact with their neighboring qubits in an array, in a lattice. And that will be enough to implement the surface code. And then also, importantly for us, the surface code can be decoded efficiently. And technically, what that means is that it admits a graph-based approximation. The decoding problem admits a graph-based approximation. So here I've drawn the surface code. This is a surface code patch at distance 5. It's the same that Alex drew before. And you can see two types of qubits, the white dots and the black dots. The white dots are the data qubits. They are the ones carrying the quantum information. And then the black dots are the ones that we are using to find out about the errors that have happened in the system. So you can see that the white dots, there's 25 of them. This is a 5 by 5 square. And they are connected by these plaquette operators, of which there's two kinds, blue and orange in my conventions. And then these operators are the operators that we use to, we measure continuously when we're doing quantum error correction, and they are the operators that will detect the errors. The blue operator, the blue plaquette implements a ZZZ operator on the 4 data qubits at its vertices, and the orange operator is the same, but with X. Now, normally X and Z don't commute, so you wouldn't be able to measure these two things simultaneously. But then if you look at the surface code, these two plaquette operators always overlap on an even number of white qubits, which makes them commuting, so you can measure them simultaneously. Now, the black qubits are there just to measure these plaquette operators, and you can see that they sit in the middle of these plaquettes. Right, so what does an error look like in this code? Well, let's imagine that the qubit at the middle here, so it's gone red, it's because it suffered an error. And I'm going to imagine that the error that this qubit in the middle has suffered is a Z error, so a phase flip. So this Z error is going to be picked up in neighboring plaquettes of the orange kind. And that's because the orange plaquettes fail to commute with the error that has happened, which is a Z error. The blue plaquettes will not see anything because the blue plaquettes are made of Z operators and they commute with the error that has happened. So this error here is going to be picked up by the 2 orange plaquettes just near it. And that means that we can represent this error as an edge in a graph. And then at the vertices at the end of the edge, we can put the stabilizers, the plaquette operators that have fired and have detected this error. So the same is true for any other Z error in any of the white qubits. And if you just draw all of this in this graph-like manner, you will find this graph where edges are the Z errors that can happen on the white qubits, and then the vertices are these plaquettes that discover the existence of these errors. So this is what happens in one time slice, but we can repeat this process over and over in time. And that's what's depicted here in the horizontal direction. This is the passage of time. And we have several snapshots of the outcomes of the orange plaquettes. We have the edges we had before, but now I've also drawn these time-like edges, which correspond to measurement errors that can happen when we do quantum error correction. And actually, if I model things even more accurately and I take into account the circuit that I need to implement to measure these plaquettes, I will draw even more edges on this decoding graph. But the point is that this is a decoding graph, and it admits graph techniques for decoding it. So just once again, this graph represents the errors in our system, the error model that we have for our system, and it's the main object we're going to use to decode the surface code. Now, there's many ways to decode an error in the surface code, and let me just briefly describe what decoding looks like. So when an error has happened, we don't know exactly what error has happened. The only thing we know is which stabilizers, which plaquette operators have fired and tell me something's wrong near me. So this is going to look like these red dots over here. But I can place these red dots on a graph, and then what I want to find is a good candidate explanation for the red dots I've seen. So that is a set of edges that explains the pattern I'm seeing here. And there's a few ways to do this. The way we're going to do it today is using so-called clustering algorithms. And what clustering algorithms do is they grow clusters around these red defects. And these clusters stop growing when there's an even number of defects within the cluster. And we can't stop growing then, because if we have an even number of defects, we know that we can pair the defects within a cluster just by connecting this even number of defects within the cluster, right? Okay, so that's roughly what a clustering decoder looks like in the surface code, and that's what our decoder is going to be doing. Okay. Now, I've presented this graph as the graph of the Z errors in our system. There's an equivalent graph for the X errors in the system, and then there's also Y errors, which you can always think as a product of Z and X errors, right? But X, Y, and Z are just errors of the Pauli kind, and that's not everything there is to life. What I want to discuss today is another kind of errors that kind of takes us outside this paradigm of errors just being Pauli type. And the error channel I want to discuss is leakage. And leakage is something that's gonna, it's an error that's gonna happen in your system if your system is not a perfect qubit and is made of a higher dimensional Hilbert space, like most qubits are. So in order to describe this error channel, I'm choosing a specific qubit type, but this also applies to other qubit types. And this qubit type is the transmon, which is basically a circuit, an electronic circuit that behaves like an anharmonic oscillator. And just like oscillators, it has an infinite dimensional Hilbert space with infinitely many states up this ladder. So we make a qubit out of this system, and then how we turn this into a qubit is we say we're going to use only the lowest two energy levels in this Hilbert space to do computation. We try to keep our system always between this 0th and first excited state. But as we manipulate our qubit, the system may accidentally leak outside this computational subspace and find itself up here in the red region. And when that happens, this is a very bad error for your system for a number of reasons. First of all, this error is silent until you measure your qubit. And it can be very long-lived, this error. The qubit may leak, and it may stay leaked for a very long time. And then what's really terrible about this is that one of these leaked qubits is going to keep introducing error in your system over and over again. And that's because, well, we don't know that the qubit has leaked, so we keep interacting with it with a 2-qubit gate, for example, with a neighboring qubit. And maybe the neighboring qubit had no error, it was perfectly fine, but then we're acting with a 2-qubit gate that is spec'd for a pair of systems that are within the computational subspace. And when this qubit is outside the computational subspace, basically this gate introduces damage in our system. So on the back of every 2-qubit gate with a leaked qubit, we're going to be damaging our healthy qubits. And this is really bad because a single leakage event can keep introducing new error in our system. And that goes against one of the fundamental assumptions that we make when we prove theorems in quantum error correction, which is that our noise is localized and decorrelated. So here is a source of a lot of highly correlated noise. And that's very bad. So whenever there's leakage in your system, you should do something specifically to target the leakage that you have. And usually what you do is you introduce a gadget called a leakage reduction unit. And a leakage reduction unit has the job of removing periodically leakage from your system. So it can take many forms, but it has one job, and the job is to make sure that if a qubit leaks, it doesn't stay leaked for very long. So here I've drawn the surface code patch again, and we have, remember, the two types of qubits. The white qubits carry the quantum information, and the black qubits are used to detect errors. So let's imagine what happens if one of the black qubits leaks. Well, that's not going to be too bad, because the black qubits are being measured all the time. And after we measure the qubits, we reset them. So if one of the black qubits was leaked, it's not going to be leaked for very long. We're going to measure it very soon, and then we're going to reset it, bring it back to the computational subspace, and the leakage is going to be gone. Now, the problem, of course, is that the white qubits, we don't want to reset them very often because they carry the quantum information, and we don't want to destroy this quantum information. So what should we do? Well, what we're doing in this paper is the following. So the surface code patch is going to look like this in one step, and like this in the following step. In one step, and then in the following step. So what happens is that we are alternating between the roles of the white and the black qubits. So in one round, the black qubits are our auxiliary qubit, and then in the following round, the white qubits are our auxiliary qubits. And what this ensures is that every single physical qubit in our system is being reset once every 2 rounds of error correction. And that means that leakage cannot live for very long in our system. It can live for a maximum of 2 rounds of error correction. Okay, so that's how we're going to deal with leakage in the first instance. We're going to introduce a leakage reduction unit that reduces the lifetime of leakage. There's more that we can do besides ensuring that leakage is not going to be super long-lived. And that's telling our decoder about any leaked qubits we have measured. And this goes as follows, right? So I have drawn here for you again the surface code patch. It's wiggling, right? It's doing this motion that ensures that leakage doesn't live for very long. And then once in a while, I can measure one of my qubits to be leaked. So when I do so, I can tell my decoder, hey, this qubit was leaked, and then the decoder can update its error model, can update the graph to account for the fact that this leaked qubit has very likely been introducing a lot of error around this measurement. And that's what these red edges signify here. Our decoder is updating its error model on the back of a leaked qubit that has been measured in order to represent the fact that errors around that leaked qubit are a lot more likely. Now notice that this adaptation, this red set of edges, doesn't go very far in the past. It's localized to 2 rounds of error correction, and that's because we're using this leakage reduction unit that makes sure that leakage is flashed every 2 rounds. So if we have seen the qubit to be leaked here, it may have done a lot of damage over the past 2 rounds. Now I will argue in the following couple of slides that doing such adaptation greatly improves the accuracy of our system. And I'm going to quantify the improvement in the accuracy of our system as the squaring of this quantity lambda. So there's a quantity that you can use to benchmark how well you're doing quantum error correction. The larger is the quantity, the better you're doing. So I'm going to claim now, and this lambda needs to be bigger than 1. And I'm going to claim that it's squared when you do this adaptivity procedure. And that's great because the squaring of lambda basically is going to mean that we can use a code that's half the distance compared to a decoder that's not adaptive. And that means we're going to be able to do the same quantum computation with much fewer physical qubits compared to otherwise. Okay, so let me argue now that lambda gets squared. And first of all, I need to give you a sense of what decoding errors look like in the surface code. And to do that, I've drawn this other patch of the surface code. This is a distance 7 surface code because you can see 7 by 7 white qubits here. And the smallest failure in a distance 7 surface code is a failure of weight 4. And this is an error of weight 4 in these qubits that I have colored yellow. So if all these qubits suffer an X error, this is going to be picked up only on this stabilizer here, this blue stabilizer with the red auxiliary qubit. And then when I tell to my decoder, hey, this guy says there's an error near me, the decoder, instead of guessing that this is the error that has happened, it's going to guess that it's the complementary error that has happened. and this introduces a logical error. And that's a feature of the surface code. Failures are of a size that's basically half the distance of the code, because it's the point at which my decoder gets confused that matches to the opposite side. And that's why when we write the performance of a quantum error correcting code, we're going to write it as an exponential function in the distance, and we usually like to write d/2 in the exponent, because it reminds us that the failures of my system have weight d/2.
Are you doing post-lecture?
No.
Then how can you do weight 4? It is a distance 6 code.
So this is a distance 7 code, and this is a failure of weight 4. It's distance 7 code because you can count as 1, 2, 3, 4, 5, 6, 7 white qubits at the top. And this is a failure, right? So you expect failures of weight 4 at distance 7. Okay, so these are the 4 errors that this is an example of 4 errors that will cause my code to fail. Now the problem when you have leakage is that instead of 4 independent errors, you can cause this failure pattern with just 2 leakage errors. So imagine now for a moment that these 2 qubits have leaked. On the back of these 2 qubits leaked, there can be a lot of noise around these qubits, and in particular, this noise string could have been introduced. And now we have, this is a big problem because now instead of 4 independent errors lining up, we just need 2 independent leakage events to line up. So actually the distance of my code has halved. So now I'm resilient to only half of the errors compared to what they would otherwise be. Now, if I am leakage aware, that means I can find out about my qubits being leaked. I can tell my decoder, hey, these qubits were leaked, and the decoder can adapt its noise model around these leakage events, and then it will know to match this error to the right boundary. Therefore, recovering the performance that we expect of having d/2 errors causing a failure. So, as I have argued, being leakage aware can square your factor of lambda. It can greatly improve your performance of your system. Okay, so this is some data just to show you that this theory actually holds when we do simulations with our decoder. And what I'm plotting in this graph is the logical error rate, so how frequently I encounter one of these logical failures in my quantum error correction code, versus the distance of the code, so the size of the surface code, the number of qubits we're using to build it. Actually, the square root of the number of qubits we're using to build it. And there's 4 curves here and 2 colors, okay? So each of the color corresponds to a different error model. Light blue is an error model with quite a significant amount of leakage, and green is an error model with less leakage. And then within each error model, we have 2 curves, the solid one and the dashed one. The solid one is the failure rate when our decoder is not leakage aware, and the dashed one is the failure rate of when the decoder is leakage aware. So I just want you to pay attention to the blue curves, and one thing you should see is that basically the blue curve here, the dashed blue curve, is roughly twice the slope of the solid curve, which in my units means that roughly lambda has squared, as I promised in the previous slide. I can tell you more about the noise model later if you're interested. Okay, so indeed we see this huge performance inaccuracy due to being leakage aware. Now I'm saying here that these are results on an FPGA, and let me just say a little bit about that now. So this is not a picture of an FPGA, this is a picture of an ASIC, which is an application-specific integrated circuit. So decoders, as I said in the beginning, they need to be implemented they need to be very performant because you want them to deal with the errors in real time, and the errors are going to come at speed in real time, right? So we need some specific piece of hardware to run our decoding algorithms. ASICs is what you would use if you had to build very many decoders and you had a lot of money to spend on this, because ASICs are cheap to make if you make them in huge volumes. But we are not in that era of quantum computation yet, so we don't have the budget to be printing lots of ASICs. What we're going to do is the closest thing that there is to an ASIC, which is using an FPGA. An FPGA is a field programmable gate array, which you can think of as a chip you can program. So it has the performance of a chip, but it's programmable, and you can reuse it for different applications. And a great thing about these integrated circuits that you can deploy in FPGAs is that they can do lots of tasks in parallel and deliver these performance and high speeds that we require to do real-time error correction. Now I will, so I'm not an engineer by background, but I work with engineers, so I can give you a flavor of what the architecture looks like. But yeah, I'm not an expert in all the details. So the thing I want to hammer home, though, is that our local clustering decoder is made of 2 bits. One is the decoding engine. So this is meant to be this FPGA, this chip-like thing that deploys our decoder. And there's going to be 2 separate units to it. One runs the decoding engine. And in this decoding engine, we're running this clustering algorithm that does the decoding. But then next to the decoding engine, we have an adaptivity engine, which runs these adaptions of the decoding graph in real time based on heralds of leakage. The decoding engine, I'm going to illustrate in this way. So it looks like an array of PEs. A PE is a processing element that you can think of as a worker that does some small computation in parallel. Okay. So the core attributes of the whole system is that it's going to be fast. It's going to have the throughput that we need to decode the surface code in real time. It's accurate and it's flexible. And flexibility is very important to us because quantum error correction is still an experimental science. People are discovering optimizations all the time. And the exact details of the decoding graph on which we're going to solve our problem depends on implementation details of quantum error correction. So for example, your choice of native gate sets, your choice of leakage reduction unit, and so on. So we want to remain flexible under all these choices. So we're going to choose a paradigm that allows this flexibility. And this paradigm is illustrated here. And the key point is that we can compile flexibly our FPGA code from the decoding graph of our system. So we intake a decoding graph, and then we output an FPGA implementation. And as I said, an FPGA is one of these integrated circuits, or something like an integrated circuit that has lots of workers that work in parallel. And then a key choice that you need to make when you are deploying such an application is how much parallelism you really need. And here I'm drawing the decoding graph that we had before. Remember, this is the decoding graph at 1 time slice for the Z or the X errors. And there's a lot of choice that we have when choosing how much parallelism we want. So on the one hand, we could have one worker per node in our decoding graph, so that all our clusters would grow extremely in parallel. This would be the fastest possible implementation of this problem, but it would be also very big, because we would need lots of these independent workers working simultaneously that would kind of occupy our FPGA. Right? On the other hand, we could have no parallelism at all and just have one worker, and that would be just like having a serial implementation of this decoding process. So what we choose to do in our implementation is to go somewhere halfway, and we're actually going to have order D being the distance of the code, nodes per processing element. And that kind of hits a sweet spot of having enough parallelism to be fast enough, but also not take all our resources in our FPGA. Okay, so this is so something else I should describe is that I said that there's a lot of parallelism in the algorithms that we use for decoding, but they cannot be run completely in parallel. So the way these algorithms work when you implement them in hardware is there's some bits that you can do in parallel, and then once in a while you need to communicate between all your parallel workers. And that is done through some careful scheduling between all the PEs in our system. And that's what this coloring means. I'll tell you more about it if you're curious. I'm running out of time. Okay, so what I showed you there was a 2-dimensional decoding graph, but the same thing kind of applies for the 3-dimensional decoding graph, in which we can see here, for example, the wiggling motion of our leakage reduction unit. So you can see these space-time edges going backwards and forwards, leftwards and rightwards, because we're wiggling our circuit. Okay, so we have this FPGA implementation of this decoding algorithm, and now I want to show you that it's fast enough. And to show you that, what I'm plotting here is the throughput of our decoder, so how long it takes to decode per round of error correction versus the distance of our code. And remember that the key figure to keep in mind here is this 1 microsecond per round, which is the throughput that we expect in the fastest qubit type, which is the superconducting qubit. And one thing that you can see here from our implementation is that for all our decoders, leakage aware or not leakage aware, and all our noise models, we remain comfortably below this threshold, so we are indeed fast enough. We have the right throughput to do quantum error correction in real time. So I'm just coming to the end now. So I've told you about the local clustering decoder, which is a fast, high throughput decoder. It's accurate because it's adaptive, and it's flexible because we compile it directly from a decoding graph. There's lots of work to do in the future, and I look forward to writing more papers about it. Thank you.
Great talk, thank you. I'm not an expert, but I'm fascinated by your suggestion that 1 millisecond unit is time enough. That seems slow to me.
It's 1 microsecond per round.
Yeah.
This is not fast compared to classical computers, but this is the fastest that quantum computers run these days, and we don't think they're going to get much faster than that.
Okay, so that's the rate limiting step, or do you expect nanosecond, picosecond timing requirement?
We don't expect that, no. Yeah. I'll say that this is the fastest technology that does 1 microsecond per round. These are the superconducting qubits, the silicon qubits, but there's other qubit technologies that are based on atoms, like trapped ions or Rydberg atoms, and these are 1,000 times slower, so 1 millisecond per round. So yeah, speed, so really the advantage you get it not because quantum computers are very fast, it's because they operate in a different paradigm.
So, I was about to say, so the trade-off is speed and parallelization. So what is how do you approach the rate limiting step so that you get maximum potential out of this?
So I think our solution, which is the decoder, is comfortably within the limits that we need. And there's a separate question, which is how fast could a quantum computer run? We don't think it's going to run much faster than these type clocks, but this is still enough to deliver groundbreaking applications in many fields.
Yeah? One question and one comment. The question is, when you describe the code that changes between data and qubit to mitigate the errors, leakage errors.
Yes.
Doesn't this introduce a complication in the computation because you keep changing the qubit? Is this an issue with that, or?
Yeah, I mean, you're right that it's a bit more complicated than the standard paradigm, but we understand perfectly how to deal with it.
There is a workaround.
Yes.
And the other comment is you mentioned superconducting qubit and atom qubit that have a time scale in the microsecond.
So superconducting is microsecond, atom qubits is millisecond.
Yeah, but have you considered photonics-based computation because they meant to be faster?
That's a good question, and the answer is no, I have not considered it.
Okay.
Yeah.
I have a question which is maybe similar to the last one, which is on the subject of the leakage reduction units. Given that you need additional qubits around the surface code patch to do that, do you still have the space you need to do operations between adjacent patches like that for surgery?
Yeah, that's a good question. So you need to make sure that there's enough routing space between the qubits in order to do this wiggling motion. And then, so something to acknowledge is that there's other leakage reduction units in the market. There's, for example, the one that Google used in their latest experiments doesn't wiggle the patch. Although Google have also looked at that. Maybe one more comment to make is that the overhead you need to implement this leakage reduction unit is subdominant, right? Because it scales only with the perimeter of your surface code, not with the area. So it's a small cost. It's a small cost, and you could choose not to do it at all because there's other leakage reduction units you can use. Yeah, Alex?
Thank you for the talk. I was wondering, do you know how this work extends? We focus on the surface code for this work. Do we know how to extend to other codes, such as QLDPC codes?
Yeah, that's another good question. this principle of adaptivity applies generically. So if you measure a qubit to be leaked, it's always a good idea to tell your decoder about that. I haven't thought very much about weakling-like leakage reduction units for other codes, and this might become subtle if you have a ratio between auxiliary qubits and data qubits that is not one-to-one.
So if I remember correctly, in your simulation, when you have physical error 3 nines, when you get to leakage aware, you get 2 order better. So suppose you do the physical error instead of 3 nines, it's a little bit off, like 0.8 or something. Did you simulate that this is stable?
We have lots more data. So one thing to say is that the advantage of being leakage aware depends on whether leakage is a dominant source of error or not in your system. If your dominant source of error is a more conventional Pauli type of error, then you gain a little bit from becoming leakage aware, but you're dominated by the other error kind. But the effect of being leakage aware boosting your performance is stable under perturbations of your noise model.
Okay, so let's thank Joan for this great talk. And,